have Ya-Qing from MIT working with Pablo Guerrero. One of the big problems with qubits in making quantum systems is that people have been successful in making qubits, but if you actually want to make some piece of quantum electronics that does something, you have to wire the qubits together somehow. And as we move from sort of quantum science into quantum engineering, that's one of the problems we need to solve. And what she started out getting her PhD from Beijing University in China, and then she's a postdoc now with Pablo Guerrero at MIT. So they're using two-dimensional materials to make optical resonators and channels in order to solve this problem.
Thank you very much for the introduction. And I'm Ya-Qing from MIT, and it's my honor to give a CIQM talk here today in Harvard. The topic today is two-dimensional materials for optical communications. So I have been working recently with these 2D materials, and this is really a big community, and there are quite a lot of interesting 2D physics. So here I'm just trying to list a few. For example, we have this one varus crystals, and because of their interlayer bonding, energy is small, and they can be easily exfoliated to atomic thin layers. And that would lead to some interesting phenomena. For example, here I'm showing like as they go to atomic thin layer, because the reduction of the screening effect between interlayers and the Coulomb interaction could be enhanced. So that's one example. And another example is as they go from 3D dimension to 2-dimensional, and their band structures of these materials can also dramatically change, and we could see a lot of novel materials and interesting physics. For example, like the molybdenum disulfide, which is a semiconductor. As they go to the thin layer, they change from an indirect band gap semiconductor to a direct band semiconductor here. And also, because of the spin orbital coupling, spin orbital locking make them have a valley selection rules. So they have been well developed recently. And another very important phenomenon is like the artificial, for these layered materials, they have the nature of doing like artificial stacking. Basically, it means we can combine two-dimensional materials from this one to another one. Two-dimensional materials itself, we can also combine two-dimensional materials with other flat surface, and it's kind of easy. And this will create a lot of building blocks for realizing novel optical electronic devices. So that's why we think it is important. And beyond this, there are also very, very interesting fundamental questions like how can we tune these two-dimensional materials, whether we can dramatically change the properties from one to another with some extra knobs. For example, we might have the electronic gate control to tune their properties. We can also tune the twisted angle between materials, and then we can create also new structures. So with this in mind, I would like to say my job was mainly focused on studying the light-matter interaction between the new systems, 2D materials, and the other systems. For example, here I'm showing like the optical transitions of layered materials. They kind of ranges from the ultraviolet to visible infrared, even down to microwaves. And the light-matter interaction can provide the fundamental information of these 2D systems. And for example, they can give your band structure informations. And also, light-matter interaction can also tell you the interaction between these layered materials and with other environments or other systems. For example, you can detect the screening effect of the substrate. You can also see the charge transfer between two layered materials. In addition to that, these are all fundamental questions. In addition to that, we are also looking for potential optical electronic applications using these 2D systems. So related to the light-matter interaction. So today in my talk, I will mainly talk about the confined light-matter interaction and nanoscales. Here I'm going to give two examples. One example is a combination of two-dimensional crystals, two-dimensional materials with two-dimensional photonic crystals waveguide. The other example is combining photonic crystal cavities with two-dimensional materials. And if I have slightly more time, I will talk about the two-dimensional phase transitions induced by the terahertz pulses. So with this, I'd like to first start with the waveguide interaction with the 2D crystals. So light-matter interaction and nanoscales has a lot of attractive phenomena. For example, cavity QED, exciton polaritons interactions, polariton condensations, as you may see in the literatures. And here what we are trying to say is a combination of two-dimensional materials and photonic crystals could bring us a new platform to study the quantum mechanics. So here first I'm going to tell a little bit about the excitons. So excitons, it exists in the solids, and it's like hydrogen atoms, but the effective mass of the excitons in the semiconductor is usually smaller than that of the hydrogen atoms. And when we add a photon to the system, and the photon could excite an electron from the conduction band to the from the valence band to the conduction band, and then the electron hole pairs they can create the excited states, and they are formed. We have excitons. And when these excitons relax, when they combine, electron hole combine, they can emit a photon, and the system can relax from excited states to a ground state. And then in a two-dimensional system, because of a natural z direction limit, the excitons are confined in a two-dimensional plane, and they can only move in a 2D plane. And because of this reduced dielectric screening, and then the Coulomb interaction is enhanced, and an apparent phenomenon that we can observe is the electron hole pair, they bond tightly, and their Bohr radius are smaller than the three-dimensional cases. So that's why we call excitons in two-dimensional materials are confined excitons. And now I also want to mention about the confined photons in the photonic crystal structures. So photonic crystals, basically, simply we can say it's a periodical nanostructures that inside the motion of the photons, they are affected like electrons in the solids. So I'm going to give you two examples to briefly understand how it works. So photonic crystal, here, the first I'm going to talk about photonic crystal cavity. Basically, we have a membrane. On the top of a membrane, we dig a array of air holes. And we have air holes. We also have a silicon membrane. And as you can see, because in the middle of this periodic structure, we have 3 holes that is missing. So we call this as a photonic crystal cavity. And you can see the optical mode are mostly confined near this missing hole area. And this is an analogy to defect states in a crystal. And so we can find in a band structure, we have a defect-like state here. So another example is photonic crystal waveguide. So basically, here I'm showing an array of the air holes, and here we have a one hole line that is missing. And because the missing line, we have a defect state. This is not defect state, this is a guided mode, which is a continuous mode, which has a distribution in a band structure like a continuous mode. And inside of this photonic crystal waveguide, because of this allow defects mode or waveguide mode, the light can be selected going through this photonic crystal structures. So now we have confined photons and confined electrons. As we combine together, what could happen? So there are actually several advantages by adding the 2D materials together with the photonic crystals. First, it is doable. This is a very important criteria because the method developed by Coulomb group, and we can easily use this kind of a dry transfer method to combine van Waals crystals to other two-dimensional surfaces. And second, when we combine a two-dimensional layered materials with photonic crystals, as you can think, these are so thin, then they will create the least perturbation to the existing photonic crystal mode. So by saying this, I mean photonic crystal, they have their certain structures, but if you add too much materials on top of them, they could be ruined. But these atomic thin layers will not, or will at least not ruin too much. Okay, so a third criteria that why I think is important is because these later materials we can tune with electrostatic gate. And this is an important knob because we can tune the carrier concentrations and even change the whole material dramatically, like the electronic properties, optical properties. And with this, I would like to talk more about my first topic, silicon photonic crystal waveguide integration with 2D materials. So this structure has a optical electronic application background, and that's why we think it is important. So as everyone has computers, as you notice that in the last 40 years, the computer speed has been improved dramatically. And this is mainly by increasing the density of transistor in your CPU or processor. But recently, this does not work anymore. The common strategy right now is integrating multiple processors, or so-called multiple cores, together to further improve your computing systems. And nowadays, this is kind of okay, but eventually, how many more cores you can integrate in your system is limited because of the heat generation and energy consumption. That will cause a final limit, and this is so-called the interconnects bottleneck. So you cannot integrate too much. So it is recently proposed that if we could use the optical communication method to replace the traditional communication method, there could be our computer could be cooler and faster. So that's why we started to thinking and working in this direction of optical communications. So here I'm giving an example. It is called on-chip optical interconnects. So the concept of this optical interconnects is simple. Firstly, you have an on-chip light source. And then the light is going through, for example, optical modulator. And the modulator will add information on this light. And the light can travel through a waveguide. And to the destination, it can be converted back to the electronic signal by using a photodetector, or it doesn't have to. So, but here, there will be one key component for this optical interconnect is the on-chip light source. So as you know, the leading technology in this optical communication field is silicon photonics. Silicon itself is not a direct band gap semiconductor. That means it is not a good emitter. It cannot work as a very nice on-chip light source. So that's why we were trying to look for something else, for example, 2D materials. So recently, it has been noticed that in a lot of 2D materials, when they go to atomic thin layers, they become direct band gap semiconductor, and they have very good quantum yield. But the thing is, for example, for the tungsten sulfide, molybdenum disulfide, these materials, their band gap is kind of large. The photon emitted is mostly in a visible range. So when they are combined with the silicon photonics, so their energy, their emitted photon will be reabsorbed by the silicon. So that's why those materials does not work. And so we started to look at the two-dimensional molybdenum ditelluride, which here I'm showing a band structure. Here, this is the hexagonal shape molybdenum ditelluride. And the monolayer limit is the direct band, and band gap is 1.1 electrovolt. This is slightly smaller than the silicon and room temperature. So this is why we started to use this. So here I'm also showing the absorption and emission properties of these materials. So it looks like it is promising, but how can we really realize it? So we started from fabbing a molybdenum ditelluride device on top. It's basically a electro gate controlled PN junctions. Here we have a monolayer molybdenum ditelluride. And then we have HBN on the top and HBN on the bottom. HBN is an insulator. Basically, here is used as a dielectric layer. And with the metal gates, we can tune the carrier concentration and carrier type in the left side and the right side. We can create, for example, if we make the molybdenum ditelluride hole doped, as you can see here, we call it the PP because it's the hole doped. And we can see this is the IV curve of the device, and the yellow curve is the hole doped region, and we can see it's roughly omega contact. It's not perfect, but it's roughly omega contact, and we have a slight contact barriers. But when we create part of it electron dope, the other part hole dope, then we could have p-n junctions. This is what we show here in the IV curve, the violet color line. We see a very clear rectification behavior. So this is a simple device that we could use, we could produce with this molybdenum telluride. Here I'm showing this is the real device microscopic image, and within the dark dashed line is molybdenum telluride, and these squares are the electrodes, and the white dashed line are the few layer graphite source and drain leads. Here we were not using metals directly to contacting this material, but graphene, because they have nice contact and they are kind of well sealing. So here I'm showing after we made a p-n junction, and when we flow a current through the p-n junction, we can have light emission from these devices. Here I'm showing two devices. One is a monolayer, the other is a bilayer. The monolayer peak is located near 1140 nanometers, and the bilayer is slightly longer, which is better because we do not want it to be too close to the silicon band gap. So the bilayer is around 1180 nanometers. So with this, we want to see, okay, what can we see out in these materials? Let's go to low temperatures and see if we could see some fine features. So first, we started to do a photoluminescence as a function of the temperature. Here, as you can see in the room temperature, we have a kind of a broad band and a small emission. As we go from room temperature to lower temperature, and below 60 Kelvin, we started to see a shoulder nearby. And then as we go lower, to 5 Kelvin, this shoulder becomes very pronounced, and we think, okay, this is something. And then we started to tune the electrostatic gate. We tuned all the two gates together, so you can see we are basically tune the electron carriers from the hole doping side to the from the electrodoping side to the hole doping side. As you can see, and the charge neutrality here, we have a neutral external emission, and the both hole doping side. Hole doping side or electrodoping side, we have two extra peaks, which is far away from the neutral external emission, and they are so-called trion or charged electrons. Basically, they are a combination of two holes with one electrons or two electrons with one hole. So you can see from this data, we can estimate it that there could be a binding energy of this charged electrons. And binding energy is estimated around 17 to 24 millielectronvolt. This means in this quantum materials, the status of the combined the status of the charged electron has a lower energy compared to the neutral electron. Okay, so we did similar things in a bilayer molybdenum telluride. Because in a bilayer molybdenum telluride interaction, we have extra interaction between the two layers. So you can see from the gate-dependent photoluminescence mapping, you can see the separation between the charged and non-charged axons. They are slightly closer, and we can do and the peak become broader, and we can do a fitting from this gate-dependent spectrum and isolated the peak position information, and we get around like 15 millielectronvolt binding energy for the trions in these systems. So with this, we understand, okay, this is interesting, and let's see what else we could see. So in our device, we actually use graphene as a south string electrodes. That means part of our molybdenum telluride are covered by this few layer graphene. Why do I mention that? Because when we started to shine a light, we can choose the region where we shine. We can shine in the area that we have the graphene, and we can also choose to shine in an area that we do not have a graphene. What could we observe? From this gate-dependent measurement, we select and charge neutrality where we have no X charge in the status. That means the carrier concentration is not playing a role here anymore. And then when compare the area with graphene and without graphene, we find that the spectrum with graphene has a red shift, which is slightly around 6 millielectronvolt. And why could we see that? So this, I will refer back to the Coulomb screening again. So basically, you have a two-dimensional material, and then you started to put on a layer of the graphene it is basically, graphene is a semi-metal. It has extra screening effect on the material. And then what we will see eventually is the quasi-particle band gap, which is the real band gap of the molybdenum telluride could shrink, which is indicated by the blue curve here. So basically, you have a 2D material, you have a band gap, but because of the screening, the band gap shift. And usually, this shift is kind of large. It's not that small. It could be 100 millielectrovolt. But here, because of the Coulomb interaction is enhanced, and binding energy here is also affected by the graphene. The binding energy of the excitons is also reduced. So effectively, what you observe is a transition from the excitons, and then the shift is reduced to as small as like a few millielectrovolt. But still, because the quasi-band gap shifting is larger, so that's why we see such a red shifted. And in low temperatures, we also see other fine features of this molybdenum telluride peaks. As you can see, if you see very carefully, you can see at the shoulder near the charge neutrality. And when we look at the spectrum, we see this is not one peak, but actually two peaks. And as we started to gate the material, the peak only happens in the electron doping side, not the whole doping side. So this is indicating saying maybe this is a defect state close to the valence band, and it's a shallow valence band, and as we gate it slightly, it will disappear. And also at the same time, when we do electroluminescence on the p-n junction, so we started to see, so this is the bias voltage from the p-n junction, and this is the spectrum. In this 2D plot, we can also see we have two peaks near the charge neutrality. So here, well, with this information, what I want to see is we start to see that these fine features. Since we do not have any other evidence, like right now we conclude them like maybe they are defects, but they could be other interesting phenomena like related to the exchange reaction in the systems. So with this, I would like to say, after full understanding of this material system, we can really see how we can use them. And now I want to go back to room temperatures. I just show you like the low temperature results, and now I want to go to low room temperatures. So basically, yeah.
I guess the question with the trion, why does that have a lower energy
than the excitons? So as you can see here, if you have an electron and hole pair, so they are basically we have a kind of Bohr radius, and their radius is kind of this size, and they are sitting together. So one must be, and one is, so let's say, on the left, and the other and right. But right now, if the Coulomb interaction is between these two material, and if right now if you have another extra charge, the extra charge can form in a certain shape, so they are not random. So and if they are like the other side, and the interaction can from the both sides. So because if you calculate Coulomb interaction, because of the screening effect of this extra charge, the total system, the energy of the total system could be lower compared to the neutral system because of this screening effect. So let's say now we're at room temperature. So what we want to do is doing some real application, and we want to make an electron light source using the molybdenum telluride integrated with the photonic crystals. So first we need a first we need something like a waveguide, and then here what I'm creating is the silicon waveguide. Basically, material is silicon, and it has a lot of air holes as a waveguide. And at one end we have a graphene coupler that is for helping us to observing the phenomenon. And then we started to put on the molybdenum telluride p-n junction on top of this photonic crystal waveguide. What we could do is, and as we flow a current through the p-n junction, the device is a light emitting diode. It's so simple. And the emitted light could evanescently couple to the waveguide. And the other end, destination, let's say, we have graphene coupler. We can couple it to our microscope, our detector, and we can see them. So this is basically the idea that we want to demonstrate that this light emitter is working. So, and then what we could do is we started to fab photonic crystal waveguide. Here I'm showing a microscopic image. In the real design, we have two grating couplers. They have the both ends of the waveguide. As you can see in the ICM image, we have nice air holes, and we have these grating couplers. And then before we put anything on top of it, we started to measure what the waveguide moves itself in this crystal structure, in this waveguide. First, we shine a broadband light source in one end, and then we collect it, and the other end, we can measure a transmission spectrum of the waveguide itself. We can see clearly here, this is transmission spectrum, and we observe a waveguide mode has a peak located at 1160 nanometers. So we verify, okay, this is the working waveguide. And then we started to put on a bilayer p-n junction made of molybdenum telluride on top of this silicon photonic crystal waveguide. So here we were using like a graphite split gauge. Previously we used metals. Here we just replaced with graphite. And we also have graphite source and drain leads. This is almost similar as what we do before. And here I'm showing the microscopic image. So in the white dashed small line here, within that area is the gate electrodes. And the p-n junction is really matching the narrow line of the waveguide here. And we can also see the same thing, every curve. As we have a p-n junction, we can see very nice rectification behavior. And we can also observe the photoluminescence and electroluminescence and room temperature and low temperature. So with this, we can see, okay, let's turn on the LED. Let's turn on the current and see what could happen. As we turn on the light, and the light is can be coupled with waveguide. And here I'm showing in a real device, I'm overlaying electroluminescence image on top of a false color optical image of the device. So basically, the brightest color in the middle is where the LED device is located. And then the pink area here is the waveguide where we were designing. And then two ends where we have the grating coupler, we observe another two bright spots. And if we zoom in at one spot, we can collect the spectrum from it and see what is this mode and how does it looks like. So basically, if you look at the yellow curve here, it is the transmission spectrum we just mirrored in the last slide, and we can see it has a peak near the 1160, and the blue line is the emitted spectrum from this waveguide. So basically, we clearly see they're overlapping quite nicely. That means our waveguide is really working as a waveguide. It travels the light from one side to another side. So it also means our p-n junction can work as a light source for such optical communication devices. And in addition to that, this is a byproduct, but it's also very nice because, as you know, p-n junction itself can also work as a photodetector. So if you shine a light into this photodetector, you will create a photocurrent. And if you measure the photocurrent, you can get the signal from, you see a light that is coming. So with this, we started to shine a laser into our device. And we have an electro-optical modulator, and this can be used to add signal to it. So basically, we started to modulate it, the light. And then the detector will give us a modulated photocurrent response, and in the end, we can observe it using an using an oscilloscope. Here, as you can see here, our device is not a DC devices, but it can work at very high speed. Here I'm showing in our device, we can work at 200 megahertz. This is quite nice, but this is not the real limit of our device, but it was actually limited by our measurement. So the impedance amplifier itself has a cutoff at 200 megahertz. That's why. And in principle, these semiconductor devices could work as high as several gigahertz. That's our fundamental limit. Okay, with this, I would like to give a brief summary about this project. Basically, we have demonstrated that the coupling between the molybdenum telluride p-n junction and a photonic crystal waveguides. And our p-n junction can work as a light emitter or as a photodetector together with these photonic crystal systems. And we also observe the excitons and the trions and the low temperature in the systems. But this is not enough. This is still far away from a real application. So what we want to do in the near future, basically, first we can do a coherent, what we want to do is a coherent light emitter. And basically, that is laser. And also, one color is not enough. So if we want to make a lot of light emitters in different ranges, then we need to develop all kinds of different materials, or trying to in different combinations of these layered materials. Okay, this is an important direction in the next step. So, any questions? Yep.
So you're going to develop lasers?
So eventually, a laser system is better, right? Because the light is yeah. So I think it's promising, and although there are a lot of arguments in this field, and people have been trying to make steps one more step to make them clear whether these lasers are really applicable in a real device. So this is an ongoing